Welcome back to the BigML tutorial series. In this video, we'll be talking about OptiML, the automatic optimization feature of the BigML platform. First, we'll discuss the need for automation in machine learning projects and BigML's solution for this. Next, we'll give a brief overview of how OptiML works in two main phases. Then, we'll demonstrate OptiML in action on the BigML dashboard with a sales use case. After that, we'll cover a few guidelines for how to select the best model, and lastly, some trade-offs and caveats that are important to be aware of when selecting and optimizing your machine learning models. As any machine learning practitioner knows, there are many algorithms to choose from, and each comes with its own set of parameters. Knowing which algorithm is best for a particular problem is challenging because the performance always depends on your data. Displayed here is the famous scikit-learn cheat sheet, which is a diagram intending to help people decide which algorithm to use based on certain criteria. Even once you've chosen an algorithm, there's still a lot of work to be done, tuning the parameters to make the algorithm work, which is difficult and time-consuming, even if you're an expert, which most of us aren't. Since BigML is all about making machine learning accessible, we naturally wanted to make this process easier. So that's what we did by adding OptiML, an automatic optimization option for model selection and parameterization. This feature makes it incredibly simple to find the best supervised learning model for your data. OptiML helps you solve both classification and regression problems, as you can include all applicable techniques, such as models or decision trees, ensembles, logistic regressions, and deep nets, or a subset of these. Time series are not included because they typically involve a different type of data structure that is best treated differently than other supervised learning tasks. After creating an OptiML, you will have a list of the top performing models for you to compare and select the one most suited for your needs. Simply put, OptiML conducts an intelligent search using machine learning to predict how well models will perform. We use meta-learning to select a good set of initial model candidates, and from there, the performance of different model types and parameters is taken as input for the creation of the next set of models and parameters. All of these models and configurations are automatically created and evaluated with the click of a button on the BigML dashboard. Bayesian parameter optimization powers this process under the hood, which we'll briefly explain on a later slide. The OptiML algorithm is split into two phases, the first being parameter search and the second is validation. Before explaining each phase, we'll introduce our use case and get an OptiML running on the BigML dashboard. For this tutorial, we'll demonstrate OptiML using a regression example of how to predict sales for Etsy shops. In case you're unfamiliar, Etsy is an e-commerce website focused on handmade or vintage items. The input data includes items sold, how many followers a vendor has, the customer's feedback, and the store's open date. This dataset is available to clone for free from the BigML gallery. Simply click the link at the bottom of this slide. Now let's check it out on the dashboard. Note that when you clone datasets from the BigML gallery, they go straight to the Datasets tab of your dashboard, so you won't find them in the Sources tab. Looking back at our dataset, we can see all of our input fields with histograms and summary statistics provided. Now we can choose to make an OptiML either by using the configuration menu or by using the one-click cloud action menu, like you can with all other algorithms on BigML. The one-click OptiML utilizes all of the default parameters and automatically selects the last field of your dataset as the objective field. If you want to change the objective field, you can do so in the dataset view by clicking the Edit button next to the field and selecting the target icon to make it the objective field. In our case, Since we cloned this dataset from the BigML gallery, it came pre-configured with sales as the default objective field, so we don't have to change anything at this point. There's one more thing to do with our Etsy dataset before creating an optimal. Since we're trying to predict sales, we need to make a linear split to ensure our training set contains past data and the test set contains future data. To do so, we'll click the configure icon and select Training Test Split. Here, we'll select the linear split option, so instead of being a random split, the data will be split sequentially based on the dates in our dataset. Finally, click Create Training Test button. Once our training dataset is finished, we'll configure an optimal. By design, optimal consists of relatively few configuration options. Selecting the objective field, or what you're trying to predict, from the dataset is essential, as with any supervised technique. For our use case, this is the sales of Etsy shops. The other main configuration options specify how extensively the optimal algorithm will run. The first is maximum training time. BigML halts a given phase of the algorithm when it goes over the time in that phase, but it guarantees that at least one iteration of each phase will complete before returning. The default max training time is 30 minutes, but keep in mind that this is an estimation and it can easily be overrun. Especially if you have big data sets, the default may be too short and you will need to set a longer time for the optimal to build and evaluate more models. The second configuration is model candidates, which controls the maximum number of different models, meaning models with unique configurations, to be trained and evaluated. The default of 128 is usually enough to find the best model, but you can set it up to 200. The top performing half of the model candidates will be returned in the final result. Below, there are more advanced configuration options that allow you to choose which type of machine learning algorithms will be evaluated among models, ensembles, logistic regressions, and deep nets. For our example, logistic regression is not enabled because this technique is only for classification problems, and we're solving a regression problem. The names can be confusing, I know. Here, you can also set the evaluation approach, the default being cross-validation, and the desired optimization metrics. For our example predicting sales, this is a case where cross-validation isn't the best option because it's likely that past data is mixed with future data in both train and test sets. So instead of doing cross-validation, we will select a test dataset, the one we previously created with our linear split. We'll go ahead and leave the rest of the options as they are and click Create Optimal. As your optimal is being created, you can monitor the progress of models that are being trained and evaluated. The dashboard will display the elapsed time, the number of models evaluated, a counter for the number of resources created, and a running series of evaluation measures using the chosen evaluation metric. By hovering over the diagram, we can see exactly how many training and test data sets have been created and how many different model types were made, and the subsequent evaluations. We'll let this run for a bit while we explain more details about how optimal works. As previously mentioned, there are two main phases to optimal. The first is the parameter search phase, in which a single holdout set of your data is used to iteratively find promising sets of parameters. On this slide is a simple diagram to show how this search works using Bayesian parameter optimization. Starting with a set of parameters, we model and evaluate each one. For example, we get a deep net scoring 0.75, a logistic regression scoring 0.56, and an ensemble that performs the best at 0.92. This information gets fed back in and influences the subsequent parameters in the queue. In this example, the order of parameters gets shuffled based on the previous results. In many cases, this process tends to lead to a good solution faster thanks to the ability to predict the expected outcome of a new set of parameters before they are executed. After finding the best performing parameters, the next phase of optimal is validation. By default, BigML only performs cross-validation on the most promising parameters, since it's an expensive process and there's no reason to cross-validate models with poor performance. This first image here is a schematic of cross-validation, which is a common evaluation method where you hold out a subset of your input data and train on the rest, and then test on the portion you held out. You repeat this process a number of times to make sure your evaluation results weren't simply by chance. As you can see in the second diagram, we start with a single dataset that gets divided into two, a training dataset and a holdout test dataset. From the training dataset, we build a bunch of different model types, ensembles, logistic regressions, deep nets, etc., all of which get evaluated and compared to the results of the holdout test set. From the many different models created and optimized, Optimal will return a list of the top performing ones. The returned list of models will depend on which optimization metric was chosen, be it the default option or one manually selected by the user. For classification problems, the default is maximum phi coefficient, taking into account all possible probability thresholds for a given evaluation. This is a better measure than phi coefficient when you have imbalanced datasets in which the positive class is the minority class. For regression problems, R² is the default. You can choose from a number of other options, including accuracy, recall, F-measure, and others. If you'd like more details on parameter optimization and metric selection, please check out the release webinar video where Dr. Charles Parker, BigML's VP of Machine Learning Algorithms, provides a deeper explanation. In that presentation, he covers this metric selection flowchart, which can help you pick the right metric for your particular problem. He also explains why cross-validation may not be a good option depending on your use case, such as the one for this tutorial. You can also find more information in the BigML dashboard or API documentation, which are linked at the end of this presentation. Now let's check back on our optimal. We can see that it has progressed to about 21%, with 16 models evaluated and 47 resources created. Given the nature of the algorithm, creating and evaluating many different models and configurations, optimals typically run much longer than any one particular technique. Since this hasn't quite finished, we'll take a look at another optimal previously made for this same dataset. This top visualization shows a bar chart of scores for the top performing models, which we can hover over and see the details. By clicking on the Summary tab, we can see an overview with the metadata about our optimal, including the total running time, resources created, data processed, etc. We can see that for our sales use case, this optimal selected 1 decision tree, 38 ensembles, and 2 deep nets as the best models. We can filter the results to only view particular model types. For example, by deselecting the model and ensemble buttons, we'll only view the 2 deep nets. Note that regardless of your use case, Optimal will only return 2 deep nets and won't iterate over them because BigML deep nets already come with 2 automatic optimization options, the first being automatic structure suggestion and the second, automatic network search. So, for any supervised learning problem, Optimal will return 2 deep nets for you to choose from, one of each optimization method. Another aspect to note is that all models comprising an optimal can also be viewed from the dashboard view for the particular model type. For example, navigating to the Ensembles tab, we can see all of the standard ensembles created manually and a separate tab for the optimal ensembles that were automatically created. Going back to the full list view, there are a few other cool things you can do with your optimal. You can filter the models based on different evaluation metrics and select multiple models using these boxes here. You can make predictions from one or more models, compare evaluations, and also create a fusion, which combines multiple models of different types. We'll go ahead and compare evaluations for the top two models, which in this case are a DeepNet with automatic structure suggestion and an ensemble that's a random decision forest. This pulls up the key evaluation metrics side by side, making it easy for you as the user to decide which model best suits your needs. Another important visualization offered from the optimal view is the importance histogram display, which allows you to compare the top 5 field importances across models. Again, comparing our top 2 models, we can see that feedback is deemed the most important field for both, but there are some differences. For the DeepNet, feedback accounts for almost 95% of predicting sales for an Etsy shop, with the number of admirers as the second most important field at about 2.3%. For the ensemble, feedback accounts for less at 74%, followed by the number of items sold at 13% and admirers at 8.7%. This visualization and all others on BigML are intended to give you as the user granular insights to how your machine learning models are performing. At BigML, we are believers of human-in-the-loop machine learning and the importance of feature engineering, which is driven by subject matter expertise in real-life situations. For this reason, we have been very intentional about the machine learning automation features brought to the platform, ensuring that they're convenient and robust, providing solutions that avoid overfitting or introducing unacceptable trade-offs. Speaking of trade-offs, here are some main factors to consider when comparing different model types. Simple models, such as decision trees, tend to be weaker and more biased, meaning that they don't necessarily have the best solution in their repertoire. But the benefit of simple models is that they tend to be more interpretable and provide higher confidence in your solution. Simple models usually have stability of fit, so you know that adding more data or adjusting the parameters probably won't cause drastic changes in the model's behavior. Complex models, on the other hand, tend to be slower to learn and predict, and they're data hungry, meaning you need lots of data to fit the model properly. The upside is that they have more representational power to understand complex problems and tend to have higher performance and lower error. Deciding what trade-offs are most acceptable will depend on your use case. For example, in some cases where you need to be able to know exactly why a model makes a given prediction, you may choose a simpler model with a slightly lower performance that is more interpretable. BigML provides the list of top models optimal created, so users have this ability to compare and contrast different models and apply their subject matter knowledge to decide which model or models best suits their use case. When it comes to selecting which model is best, it's not as trivial as simply picking the number one model returned from optimal. There are several factors to consider in addition to performance. One is retraining. Will the amount of data change over time? Whether you'll be retraining with more or less data in the future will dictate which type of model will respond best. Another factor is fit stability. Does your model need to be invariant to small data changes? If so, you'll probably want to go with a simpler model. Also consider prediction speed and what amount of latency is acceptable. The differences here can be orders of magnitude. For example, if you're comparing a logistic regression to a DeepNet, The DeepNet is making thousands of calculations for every one a logistic regression makes. So, if your application requires millisecond latency, say an IoT monitoring application, this is something you need to consider. Next, here are a few caveats to keep in mind when using OptiML. The first is that BigML had to define a search space that would suit most datasets. Therefore, if you have an edge case or an unusual dataset, the right model for your data may not be in there. These cases are far and few between, but it is possible. The second is that model selection tends to require a lot of data, so the more accurate you want your OptiML to be, the more data you will need. As a metaphor, you can think of OptiML like a one-stop shop. As a local convenience store provides basic items such as food, drinks, toiletries, etc., that serve a range of customers and situations, OptiML is like a one-stop shop for supervised machine learning problems. It offers multiple algorithms with many configuration options that can be mixed and matched to suit the needs of many predictive use cases. What's more, this OptiML shop comes with an easy button, so instead of having to go into the store and look around for what you need, you can get a whole bunch of models all created and optimized with the one-click menu option. Pretty good deal, right? Before we wrap this tutorial up, we want to share an example of OptiML succeeding in the wild, if you will. David Gerster, a strategic advisor at BigML, entered a Kaggle competition to predict house prices using advanced regression techniques. David used BigML's OptiML, and his submission reached the top 5% of the competition. We share his own words below. All I did was clean up the data a little and push the OptiML button. Super ultra amazing product. This is the power of OptiML. With minimal effort and time required, any machine learning user can create top-performing models to solve their use cases. To summarize this tutorial, we learned that OptiML provides automatic optimization for model selection and parameterization. Automating these processes saves time and effort for any machine learning practitioner, whether you're an expert or just getting started. Through Bayesian parameter optimization, OptiML creates and evaluates various models, each with unique configurations. While OptiML removes much of the tedious and manual work, there is still the need for subject matter expertise and human intervention, or human-in-the-loop machine learning. Overall, OptiML can help you solve many supervised learning problems. For more information, please check out the links provided on this slide, including the release page, which contains the blog post series, and the detailed documentation for the BigML dashboard and API. Thanks for watching, and we hope to see you at the webinar for our next release.